The next PowerPoint is going to look at pressure and resistance. We're going to explain the effects of vasoconstriction on resistance and blood flow, blood volume and blood pressure. You should be able to define after this PowerPoint, you should be able to define pulse pressure and the factors that affect pulse pressure. We're also going to talk about compliance, what it is, and the factors that can decrease compliance. Okay, so vasoconstriction refers to the process by which some blood vessels become smaller. And that happens when the smooth muscle in the tunica media is constricted. The sympathetic nervous system, for example, innervates the tunica media smooth muscle of muscular arteries and arterioles, especially those blood vessels of the periphery of the body, peripheral blood vessels. When there is sympathetic stimulation of those blood vessels, they vasoconstrict. Vasoconstriction decreases blood flow. And the effect of vasoconstriction that has on blood flow is because it increases resistance. Remember that blood flow, the relationship between blood flow and resistance was an inverse one. When resistance increased, blood flow decreased. Vasoconstriction increases resistance, therefore blood flow decreases. Vasoconstriction decreases the volume of blood flowing through the area by decreasing the blood volume. And in decreasing blood volume, it decreases blood pressure. So you should know that as you decrease the blood volume, blood pressure is going to decrease. And you can start thinking about these again as a hallway through which runners are running. If you make the hallway smaller, fewer people at a time can run down the hallway. Therefore, because there's less people, there is less chances of them bumping against each other and bumping against the walls of the blood vessel. Therefore, blood pressure decreases. The relationship between vasoconstriction and blood flow is not a one-to-one relationship, meaning that if we decrease the size of a blood vessel by a factor of 1, blood flow does not decrease by a factor of 1. The relationship is the effect that vasoconstriction has on blood flow is to reduce it by factors of 4. If you look at the equation that explains why this happens, is because we are looking at the radius of the blood vessel elevated to the power of 4. So when a blood vessel size is decreasing half, blood flow decreases by a factor of 16. So as we decrease the radius of a blood vessel, we increase the resistance by a factor of 16, which means blood flow decreases by a factor of 16. So it will be 1/16 the blood flow that would be otherwise. So this is to explain that the decrease in blood flow that brought about by vasoconstriction decreases blood flow by 16 times 4 times the size of the vasoconstriction. Pulse pressure is the difference between diastolic and systolic pressure. So if the systolic pressure is 120 millimeters of mercury and the diastolic pressure is 80 millimeters of mercury, pulse pressure at that point would be 40 millimeters of mercury, 120 minus 80. And this will be the pulse pressure at the aorta, which is the largest blood vessel. I should say the largest artery. As the blood vessels decrease, so does pulse pressure until it pretty much disappears. So in smaller arteries, pulse pressure will be smaller because the difference between systolic and diastolic pressure will decrease until by the time we get to the arterioles and the capillaries, pulse pressure has completely disappeared, which is exactly what we want. The reason why pulse pressure is greater at the aorta is because this is one blood vessel that is receiving all of the stroke volume that is pumped out of the left ventricle. However, as the blood begins to circulate, that one very large blood vessel begins to divide into many smaller ones, so that there will be less blood flowing through these vessels. And so even though they do become smaller, they become more numerous, so the blood is distributed among smaller and smaller hallways. So again, going back to the analogy of runners in a hallway, you start with 100 runners down a hallway, and the hallways begin to branch, and some of them begin to distribute themselves among these other branches, even though the hallways become smaller because there are fewer runners. And as the hallways become smaller, the runners begin to go slower and slower. Blood pressure decreases, and the runner begins to run at a slower pace because the space has become tighter. And that's exactly actually what we want. We want that to happen because ultimately the function of the circulatory system is to be able to exchange substances between the blood and the tissues. So notice that at the capillaries, there is no pulse pressure, which means that there is no difference between systolic and diastolic pressure. Blood flow is reduced tremendously at that point, so that blood is traveling very, very slowly, which is exactly what we need for the diffusion of substances between blood and tissues to take place. Diffusion requires time, and if blood was flowing very quickly, there would be no time for diffusion. So we want the blood flow to slow down so that diffusion of substances back and forth can take place. As we go to the venules, blood pressure, pulse pressure will again continue to be very, very low. Factors affecting pulse pressure will be the stroke volume. Again, because it has to do with the force of the stroke volume with which the left ventricle pumps the blood out. The more blood volume, the bigger the stroke volume, because the ventricles are going to increase contractility. So exercise is one of the events that increase blood volume, increases contractility, therefore increases stroke volume, and with that, the pulse pressure increases. Compliance is the ability of a blood vessel to stretch in response to pressure. That is something that happens in arteries, especially the elastic arteries. The aorta is going to stretch as it receives more blood, and in order to accommodate the extra volume of blood. However, as we age, blood vessels become stiff and less compliant. So as blood vessels decrease their compliance, they are not able to stretch when they receive more blood. Therefore, blood pressure increases, and that increases pulse pressure. So imagine again the hallway, lots of runners, but the hallway is able to stretch and enlarge as the number of runners increases, so that the pressure of the runners bumping against each other doesn't significantly increase because the hallway has become bigger. But if the hallway is not able to become bigger all of a sudden, when the left ventricle pumps blood out, that extra volume of blood will create more pressure as it bumps against each other and the walls of the blood vessel. So, an increase in pulse pressure as we age is typically a sign that our blood vessels are becoming stiff and they're not able to accommodate the extra pressure, especially the extra systolic pressure. We typically measure blood pressure in the radial artery, but there are other locations like the femoral artery, the popliteal artery, the carotid, etc. So which types of blood vessels, which types of arteries, veins, and capillaries can vasoconstrict in response to neural or hormonal stimulation? And we haven't really talked about that per se yet, but we will. We have mentioned, however, that it is the sympathetic nervous system that is going to cause the constriction of blood vessels, which means that it will be the sympathetic hormones, epinephrine and norepinephrine, that will have the same effect. So it is the sympathetic nervous system that innervates blood vessels. Oops, didn't mean to do that. Let me go back. Okay. You should know what pulse pressure is, and why does pulse pressure decreases in the veins? Why does pulse pressure increases as we age? And now keep in mind, in veins, the opposite is happening as happens in arteries. We go from many small blood vessels into progressively fewer but larger blood vessels as the blood returns to the heart. And you should know the effect of exercise on pulse pressure. And why do we measure pulse pressure using arteries is because veins don't have a pulse pressure. Compliance, we talked about that before, is the ability of a blood vessel to accommodate large volumes of blood. So we're going to talk a little bit about compliance and veins. So the easier it is to stretch a vessel, the greater its compliance, the better it can accommodate a greater volume of blood. So veins are called compliance vessels because they're easily stretched and they can hold a great volume of blood. Think of a balloon versus a tire. A balloon can expand easily with just a little bit of pressure by just blowing in it. A balloon is very compliant. A tire, on the other hand, it's not very compliant. You have to put in a lot of air to be able to expand it. So veins are like balloons. They're easily stretched. At any given time, about 84% of the total volume of blood is found in systemic circulation. That means it's not in the heart or the lungs, but is actually flowing through the body. Out of that, 16% is found through the heart and lungs, okay? So out of that 84% that is circulating through the body, 64% is found in veins. A lot more than half of it is found in veins. So veins are called compliance vessels. That is one way in which the body is going to store blood, is by pulling it into the veins. So what is the relationship between compliance and blood flow? The greater the compliance, the slower the blood flow. Because there's no difference in pressure between point A or point B. Describe the velocity of blood flow at capillaries, arterial and venous side. The blood flow once we get to capillaries, blood flow has diminished tremendously. Between arteries and veins, blood flow pretty much doesn't stagnate, but it slows down even more. And we talked about what happens with the beginning of circulation when we have one blood vessel that branches into many smaller ones, and then that is going to affect blood volume and blood flow because we're going to have less blood circulating into smaller vessels, which is going to slow down the flow of blood and the velocity of the flow of blood.